So, hello everyone. Today we are happy to have two speakers to present their researchers in the high energy seminar. Our first speaker is Dr. Stefano Marchesi. Dr. Marchesi is a researcher at the Italian National Institute for Astrophysics, INF-OAS, in Bologna, Italy. His research focuses on accreting supermassive black holes in the center of galaxies, and particularly on the most obscured among these sources. He obtained his PhD in astronomy in 2015 at the University of Bologna. During his PhD years, he was a visiting graduate student at Dartmouth College, the Yale Center for Astronomy and Astrophysics, and at the Center for Astrophysics, Harvard and Smithsonian. After graduating, he has been a postdoctoral fellow at Clemson University from 2016 to 2019. Today, he will introduce to us the distant and obscured supermassive black holes, discovering the missing AGN populations with current deep surveys and the next generation X-ray telescopes. So Stefano, the floor is yours. I will alert you 2 minutes earlier.
Thanks a lot, Shuri. Thanks a lot, everyone. Thanks for inviting me. It's a pleasure to be here and give this talk. So this talk today will focus on two papers that I worked on in the past years. So the first one is this paper recently published on ANA, and which is focused on J1030 field. But first, just a brief introduction on the broad scientific goal. So the search, the X-ray search in particular for early supermassive black hole accretion. We know now that the early, with early is, I mean in this case at redshift greater than 3, accretion on supermassive black holes is expected to take place in a heavily obscured environment, as shown, for example, in this picture by Vito et al. The fraction of AGN that are obscured at redshift greater than 3 up to redshift 6 is around and above 50%. So characterizing heavily obscured AGN is key to get a complete census of the AGN population. In the local universe, this can be done with several facilities, but in particular with NuSTAR, and there are several works, for example, by Shuri Zawi himself, who showed that you can really do the best characterizing the population of heavily obscure sources where the emission is dominated here by the Compton amp above 10 keV with this instrument, NuSTAR. Moving towards higher redshifts, though, the Compton amp moves in the energy range covered by facilities like Chandra and XMM, and therefore studying these sources between 0.5 and 10 keV becomes ideal. So now there are many different approaches to find AGNs in the X-rays, but one of the most exploited are certainly surveys, so targeting a certain portion of the sky with deep observations. One of the fields that has been targeted most recently is the J1030 field. This field is centered around a QSO at redshift 6.3. This field is also the first field where a spectroscopic overdensity was confirmed at redshift 6.3, and another overdensity is observed in the same field of view at redshift 1.7 around FR2 radio galaxy. A 0.5 megasecond observation with Chandra led to the detection of about 250 sources. This makes this field the 5th deepest field among the various fields. This is a classic X-ray plot with the flux achieved by the survey as a function of the area covered by the survey itself. The majority of these sources are extragalactic objects, and for about 50% we got a spectroscopic redshift. The remaining have a photometric redshift. The photometric redshifts were obtained taking into account the fact that the field has been covered by a variety of facilities in the optical and the near infrared. There are also radio observations with ALMA and in the millimeter with MUSE, but this is outside the purposes of this talk. But still, the field has been extensively studied. Overall, we achieved a good photometric redshift reliability, particularly if you don't take into account broadline AGN, whose characterization and finding a photometric redshift is always more complicated due to the particular SED. The number of outliers, meaning photometric redshifts and spectroscopic redshift in this agreement, is fairly low, and especially it's consistent with other survey like the Lockman-Hall and Stripe T2X, for which the number of bands and photometric points used in the work was similar, and in particular for the lack of narrow band photometry, which is key to properly constrain the photometric redshift, especially for broadline AGNs. So if you want, this catalog is available online with all the spectra, CDs, and so on. This is the link. Please take a look. Use the data. We are happy to share with the community, and if there's some particular work that you want to do with the catalog, just let us know, and we are happy to collaborate. So now focusing on the high redshift sample, as I mentioned, the issue here is that while there's a fairly large population of sources in J1030, which has a redshift greater than 25 sources, only 3 of them have a spectroscopic redshift. For all the other objects, there is only a photometric redshift, which means that we cannot do science or estimates of the properties of the sample using the nominal value of the photometric redshift, but we need to use the probability distribution function. So this is an example of a source whose redshift nominally is 5.7, but really it's just a lot of upper limits in up to the near infrared and only a detection in the IRAC band. This suggests that the source has to be at a high redshift likely, but really rather than having a nominal value of 5.7, really we already have a lower limit redshift around 2. So we cannot use the nominal value to do computations of the X-ray luminosity function or the space density and so on, but we can use the probability distribution function of the redshift to use this information in a more consistent way. So we computed number counts, so the number of sources at a given flux, a redshift greater than 3 and greater than 4, and compared the results that we obtained with different models and AGN population synthesis models and different results coming from surveys like Chandra Cosmos Legacy or more recent works by Fabio Vito and collaborators. And we found evidence for an overdensity, particularly redshift greater than 4 here. These two, the red and the blue squares are obtained with 2 different photometric redshift codes, which suggests that it's not something due to the code itself, but it seems a result that really is there. But of course, this result, this intriguing overdensity, because this will be another overdensity in a field which we know is already overdense, redshift greater than 6, this overdensity needs to be confirmed with a spectroscopic campaign. Luckily, we got time with the LBT, and so observations are being taken this week to target with MODS, which is a multi-object spectrograph, the population of redshift greater than 3 targets. In particular, in the end, we're going to have a redshift, we're going to target about 50% of the redshift greater than 3 candidates. So, of course, this is an intriguing result. It needs spectroscopic confirmation, and it shows that indeed X-ray surveys are efficient to search for high redshift population. But we are sort of limited really to the redshift greater than 3, redshift greater than 4 population, and really not a lot, actually not at all can be said a redshift greater than 6, which is where most of the exciting stuff happen, when the first supermassive black hole really are accreting, and we really want to know more about them to understand also, black hole seeds and all this type of stuff that we cannot really do at the moment with current X-ray surveys. So in the second part of my talk, I would like to do some presentation of a paper I published last year with collaborators, where we presented the new mock catalogs of AGNs, galaxies, and clusters, and we tested them to simulate surveys with Athena and with the AXIS probe. So these mocks have been built to simulate X-ray surveys with the 6th software, which is a very flexible software to perform simulations of surveys with any type of instrument, both instruments that are already available and instruments that are going to be launched in the future, possibly, or even probes like AXIS. And so these mocks are based on both observational data, like the X-ray luminosity function obtained by Vito et al. In these 2 papers that are reported here, and are based on the deepest X-ray surveys, such as the Chandra Deep Field South 7 megasecond. And these mocks are based also on population synthesis models, and in particular, we chose the Gili et al. 27 model, which is a model based on the modeling of the cosmic X-ray background with an underlying population of AGN, unobscured, moderately obscured, and heavily obscured. All these mocks are publicly available. This is the link to the web page. You can download them and use them again for any type of purposes, for simulations of if you're planning to do propose for surveys with Chandra or XMM, or for more specific type of works, you can do that, or also if you want to test new instruments. So at the moment, I'm also working on a catalog of non-active galaxies based on a recently published infrared mock, the Spritz mock by Bisigello et al. 21. So the idea so far, the mock that we built for non-active galaxies was based only on the number counts obtained in the X-rays. Here, this is an infrared mock that has been built for surveys in the infrared, and for which we determined the X-ray luminosity based on the amount of X-ray binaries and the diffuse gas derived by the star formation rate and the mass of the host galaxies. So using equations that link star formation rate and host mass to the luminosity in the X-rays, we derived luminosity in a much self-consistent way. This catalog is going to be published during this year. So now we need new facilities. As we said, really we need X-ray surveys to detect these accreting supermassive black holes in the early universe that are extremely obscured and extremely faint. But we also know that current facilities are now, they have done probably a lot of what is possible to do. In particular, as you certainly know, of course, I don't have to mention it here, Chandra is suffering of a worsening in effective area below 1 keV, and this limits its efficiency as a survey instrument, particularly for high redshift sources where you really need the soft X-ray given the redshift of the spectrum. There's a new XMM Newton, a much better XMM Newton, which is being developed is Athena, but at the moment there's no X-ray instrument with the exquisite Chandra-like spatial resolution that has been cleared for development. This might change with different facilities, of course. There's links that will be the ideal instrument to do all the things that I mentioned and much more. And another facility that that has been proposed is the probe AXIS. A white paper has been submitted to the NASA 2020 Decadal Survey, and the big strength of AXIS is sub-arc second resolution, as you see here. This will be below 1 arc second over the whole field of view of AXIS. So this would be like Chandra on AXIS, but then going off AXIS, of course, Chandra decreases its efficiency, its alpha energy gets worse very quickly. AXIS would be stable across the whole field of view. And this would work excellently in together with Athena. Athena would have a worse PSF, probably even worse than this. This was done in 2020. It seems it's going to be even worse, but it will have an excellent effective area. And so Athena will collect a lot of photons, which is also ideal for surveys, but AXIS would have a sub-second resolution, which would put the background almost to zero. And this is also extremely important for X-ray surveys. So, as you certainly know, recently there has been a call for instruments to be proposed either in the far infrared or in the X-rays, following the input by the Decadal Survey that mentioned that an X-ray mission should be done that should complement the Athena mission. So certainly this can be many things. It's general, of course, but certainly an instrument with sub-arc second resolution would be an ideal companion for Athena. So this is a summary of the results that we obtained with our simulations of what could happen in the future, what could be the landscape of future X-ray surveys with AXIS and with Athena. And there will be really a new space of parameters to explore. Once again, this is the flux of the surveys. This is the area covered, and there will be an increase which will be huge with respect to what we have currently. Of course, links could be even much better in this regard, could go even deeper than AXIS, and also starting sampling a population of sources that so far has been invisible, and really finding the first, for example, black hole seeds at redshift greater than 10. So to summarize quickly what AXIS and Athena could do in synergy, these are the results of the simulations that we performed. AXIS, of course, this is very general and things can change, but for the proposed surveys with AXIS and Athena, overall, we expect to detect about 500,000 AGN, assuming no overlap between the two surveys. And 90% of these sources will be detected for the first time in the X-rays. So this would be really a new era of discoveries that would be extremely exciting for the whole community. In particular, the AXIS deep field will be the first X-ray survey where non-active galaxies, so sources where the AGN is not the major contributor, will be the most part of the population. Of course, such surveys, such a new fainter window of discovery would be a big challenge, not only for the X-ray community, but for the whole community. In particular, identifying counterparts and measuring redshifts would be a huge challenge. And this will require, of course, new optical and near-infrared missions, such as, for example, the LSST and the Roman Space Telescope. These surveys, in principle, would also nicely work complementary with James Webb in the identification of heavily obscured AGN, but the timeline will be challenging. We hope James Webb will be up in the sky in the mid-30s when Athena will be launched, but we love to see, of course. And just to finish, so let's take a look at what Athena and AXIS could tell us regarding the high redshift universe. Of these 500,000 sources detected by AXIS and Athena, up to 20,000 will be a redshift greater than 3. Just to give you an idea, there are fewer than 500 that are detected in all the current X-ray surveys combined. So the increase will be enormous, really. This would be a whole new type of science. And once again, Athena and AXIS would work very well together. Athena should detect more sources overall and have more counts per source. So this would allow, for example, for spectroscopy at redshift greater than 3. But on the other hand, AXIS would detect this whole population of intrinsically less luminous sources that would be missed by Athena. So once again, there would be an excellent agreement and complementarity between the two. For the first time, it will be also possible to track accreting black hole seeds up to redshift 8 and 9, and this will open a whole new window for science, given that these shown in cyan and blue are AGN currently detected in the X-rays, and there are none of them basically redshift greater than 7.5 or so. And so to conclude, this will also allow for a huge improvement on the determination of the X-ray luminosity function, redshift greater than 3, greater than 6 and above, sorry. There will be enough sources that at redshift greater than 7 that it will be possible to constrain the X-ray luminosity function with unprecedented quality. This is an example redshift between 7 and 8 in the combination between AXIS in black and Athena in red. And the shaded area that you see here are the predictions of theoretical models reported in a recent paper by Amanantidis et al. So this is all the possible range of predictions that theoretical models currently have. So really, there's a range of uncertainties that is enormous, because of course we really have nothing from an observational point of view to validate these models. So AXIS and Athena would allow for an unprecedented tuning of these theoretical models, and will allow for the first time to rule out many combinations of parameters for these models. So this concludes my presentation. So I hope I convinced you that the study of obscure accreting and supermassive black holes at high redshift, it's really an ideal scientific topic for X-ray surveys, deep X-ray surveys, with current and especially with new facilities. I've shown that one of the fields that we can exploit to do science with current facilities is the one centered around the redshift 6.3 QSO J1030, because overdensities offer an opportunity to detect more sources and therefore to have a better characterization of a population that is otherwise extremely elusive. And in general, deep fields are still the best way to go with the instruments that we have at the moment if we aim to find heavily obscure redshift sources. For example, in J1030, there's a hint of an overdensity redshift greater than 4, but this needs to be spectroscopically confirmed, and we hope to do that in a few weeks. For the future is new facilities. Athena is going to be launching in the mid-30s, late 30s, but it needs a companion like AXIS, a companion like Lynx, to open a new X-ray window on the high redshift universe and really change what we know are redshift greater than 6 and in the first billion years after the Big Bang. The unprecedented source statistic in this redshift range will make possible to put stronger constraints on theoretical models and enhance the synergy between theory and observations. This concludes my presentation, and if there are any questions, they are welcome. Thanks.
Thank you very much, Stefano. Great timing. And so I didn't see any question in the chat, but if you have a question, please raise your hand. So I didn't see a hand, but maybe I can ask a question at first. So great talk, Stefano. I have a quick question. So could you comment more on the non-active galaxies that you are going to probe or study in this year? You are muted, Stefano.
Okay, sure. Yeah, so the idea here is that we have this mock called Spritz that has been built starting fitting infrared luminosity functions of both AGN and non-active galaxies. So we used these mocks. We took away the infrared population, the AGN population. We focused on those sources where no AGN was contributing significantly, and these mocks have many parameters, the SED from optical to far infrared and so on. And also one of the parameters is the star formation rate and the mass of the host galaxy. Now we know from several papers, for example, some works by Lemmer et al. We put constraints on the X-ray luminosity function of non-active galaxies and found trends between the star formation rate and the host mass and the X-ray luminosity. So we used these trends to derive X-ray luminosity function, X-ray luminosities for our sources, for the sources in Spritz, and then those were converted in fluxes, and then these were in the end used as an input parameter for our mocks. So now we are performing simulations exactly like these that I've shown you. So we are resimulating everything, but with these new mocks, and we want to see what AXIS and Athena could do in terms of detection of non-active galaxies.
Thank you. So we still have a few minutes. Yeah, please raise your hand if you have questions to Stefano. So I think our audience may still need some time. So maybe I can ask a second question. I'm very interested in your redshift 6 quasar. So do you have, for example, the other information of this source, like the black hole mass, Newton ratio, and other wavelength properties of this source?
Yes, there are several works on this object. It has been studied extensively. So in the X-rays, there's a work by Nanni et al., the same author of the survey in 2019, and variability has been found for this source, which is commonly observed. And this was something that has been done in the X-rays. Also, more recently, there are works by Mignoli et al., which were able to find the presence of Lyman-Breck galaxies around the QSO, and spectroscopically confirm for the first time an overdensity redshift greater than 6. So this suggests that the quasar is causing positive feedback on the nearby environment and creating star formation and enhancing these galaxies that otherwise will be non-detected, would be non-active with a much smaller star formation. So yes, there's a lot going on the quasar. There are also detections at other wavelengths, but yeah, the most recent result is this one by Mignoli et al. 2021, which shown that indeed around the QSO there's a positive feedback, and the environment is benefiting in a sense of the quasar activity.
Thank you so much, Stefano. That's very interesting. I think we can go ahead to the next speaker, and so please ask your question in the chat if you have any for Stefano. And so our next speaker is Annalisa Bonafede. Dr. Bonafede obtained her PhD at the University of Bologna in Italy in 2010. She was a postdoc fellow in Germany from 2010 to 2014. She was a junior professor in Hamburg University from 2014 to 2016. She is an INAF research staff from 2016 to 2018, and an associate professor at the University of Bologna from 2018 to now. Dr. Bonafede is interested in radio low frequency observations and polarization data to study magnetic field and particle acceleration in clusters of galaxies. She is the PI of a European Research Council starting grants from 2017 to now. Today, she will tell us about the magnetic field and the particle acceleration in galaxy clusters, news from LOFAR observations of the Coma clusters. And so, Annalisa, the floor is yours.
Okay, thank you. Yeah, thanks for inviting me to give this seminar. Would have been much nicer in presence, but that's what we get. So let me start with a brief introduction about galaxy clusters, what they are. In optical, they look like hundreds to 1,000 galaxies in a region of roughly 910 megaparsec QO space. But if you look them in the X-rays, we actually detect hot gas that has a temperature of 10 to the 7, 10 to the 8 Kelvin. It is very diffuse and diluted, and we actually observe it in the X-rays through thermal Bremsstrahlung emission. And these are common properties that all galaxy clusters have. Something that we observe instead in radio that is not common to all galaxy clusters, but just to some of them, is a diffuse emission that spans all the cluster volumes. So it's on megaparsec scale. And this emission is synchrotron and probes that there are magnetic field and relativistic electrons that are spread in between the galaxies in the intracluster medium. Now, this emission, as I was saying, is only detected in some clusters and can be detected in mainly 3 flavors. We have mini halos. You have an example here on the top left, where you see the radio emission in colors and the X-ray emission in contours. So we have mini halos that are detected in systems that are virialized, so close to the dynamical equilibrium, and they span hundreds of kiloparsec in size, so they are restricted to the cluster core. In merging systems, instead, we see other 2 types of radio sources called radio halos. You have an example in the central panel where radio emission is in magenta color. And it's an emission on megaparsec scale that coexists with the thermal emission from the gas. And in this merging system, we also have systems with also have another type of radio emission. You have an example on the right panel. This emission has an arc-like shape morphology. You see the emission in blue here. And this is what we call the radio relics. So by studying the radio properties of clusters, we are basically tracing the coevolution of the non-thermal components, so magnetic field and cosmic ray electrons, together with the cluster dynamics. Now, what's the problem in explaining these sources? It's a problem that is there since they were first discovered many years ago. If we compute a lifetime of electrons in a magnetic field that has more or less the strength of a microgauss or so, the lifetime is the order of 10 to the 8 years because the electrons radiate their energy through mainly synchrotron and inverse Compton losses. They can diffuse at a velocity that is roughly hundreds of kilometers per second. And so they should be able to cover distances that are no larger than tens of kiloparsec in the intracluster medium. While instead, as I was showing before, we observe the radio emission on scales of a megaparsec. So we have a problem here, meaning that the particles, the electrons, need to be either continuously injected in the intracluster medium or continuously accelerated locally in situ in order to be able to produce emission on such a large scale. What has been proposed to explain the sources is that during cluster-cluster mergers, there is a large amount of quantity of energy that is injected in intercluster medium. So when two massive clusters merge, we have 10 to the 64 ergs released in the intercluster medium. Most of this energy is thermalized, so goes into shock and heating the gas. But a small fraction of that could be channeled in turbulence that could reaccelerate particles through very complicated magneto-hydrodynamical phenomena, and part of this energy could be channeled in shocks. And these shocks could propagate from the center of the cluster to the cluster periphery and form what we see in radio as this arc with this arc-like shape morphology, and that we call radio relics. When I say that the efficiency of these, it's a small fraction of energy can be channeled into this non-thermal component, I mean really that from physics we know it should be of the order of few percent. So the problem is now trying to understand if we have enough energy to power these sources. And mini halos instead should be powered by other mechanisms. They are in clusters that are virialized, as I was saying before. And so far there are two models that have been proposed. One possibility is that when clusters undergo minor mergers, the core could be sloshing in the potential well of the cluster, and some turbulence could be triggered and reaccelerate the particles here. So in a mechanism that is similar to the one we used to explain radio halos, or they could have an hadronic origin, meaning that we have collisions between thermal protons of the gas and cosmic ray protons that should decay in a number of particles. Among these, there are pions, and these pions should decay after several other decay chains that I haven't written here, in electron and positron pairs. And these electrons could originate the synchrotron emission when they interact with the magnetic field. So this is basically the general picture that was proposed since these sources have been discovered. Now, some of the open questions that still remain to be addressed, just the one that I will try to address somehow here in this talk, is how does actually turbulent reacceleration work? There are several turbulent modes that could accelerate particles. And in particular, models so far are focused on compressive and solenoidal modes that would accelerate cosmic ray electrons. And as I was saying before, since this the efficiency of turbulence is anyway very low, it needs to act on electrons that are already pre-accelerated by some mechanism. So it is possible that there is a role of AGN in the intercluster medium that could release electrons throughout their life. And these electrons could form a fossil population that could be easily reaccelerated by turbulence. What do we need to answer these questions? Since these sources have a low surface brightness emission and they have a very steep spectrum, we have to go to low frequency radio observations to observe more of them and to test the predictions of the models. We can say through this sketch that at high frequency, so you have the frequency on the y-axis here, we are observing the most energetic events. So it's really just the tip of the iceberg that is revealed at 1.4 gigahertz. And as we go down in frequency, we are looking at long-living cosmic ray electrons and weak magnetic fields. And we're actually seeing the bulk of population of this component. Here we have an example of cluster. You see on the top the emission at 1.4 gigahertz, and on the bottom the emission at 140 megahertz. And you see that as we have the chance to detect lower and lower energy emission, we see the emission that on much larger scales. So we started observing these objects with LOFAR, the low frequency array, and there were some important new discoveries. For instance, we found a 3 megaparsec bridge of emission that is connecting to massive clusters of galaxies in these pairs Hubble 399, Hubble 401. And these results that was published in Science prove that there are magnetic fields and relativistic electrons even outside the clusters, posing new challenges to models that already had troubles in understanding how this emission could be generated in the cluster centers. And another unexpected finding that we discovered is by my former postdoc, Marisa Brienza. It was published in Nature Astronomy at the end of last year. In this group, we found a very complex emission of filaments and threads of radio emission. It's a small galaxy group, so order of 3, 7, 10 to the 13 solar masses. And we see here multiple generation of bubbles, and that preserve the integrity over hundreds of kiloparsec, probably under the influence of magnetic fields. And we see several episodes of these bubbles here in this beautiful picture, and they're all dominated by buoyant uplift and do not mix immediately with the gas. So through this mechanism, they could be able to exert feedback on the intracluster medium to very large distances, larger than we thought before. And this is also telling us that the AGN actually does spread electrons, cosmic ray electrons, throughout the medium during their lifetime. So among all the clusters, I can skip this, sorry. Among all the clusters, we focused our attention on the Coma cluster. This is one of the most famous and best studied clusters, also in the radio band. And it was the first cluster where a radio halo was found. Here you see an emission from the LOFAR survey. So LOFAR is a low frequency radio interferometers located in Europe. This image is centered at 144 megahertz. And this consists of two joint deconvolved observations of 8 hours each. You see several sources here. You see the center of the Coma radio halo, a group that is now moving toward the cluster center, and the radio relic at the bottom right of the image. Now, if one subtracts all the sources and reconvolving at lower resolution, we can see that actually the emission of this, the non-thermal emission, covers very large extent. We detect in this cluster, we confirm, to better say, the detection of a halo front, so a sharp discontinuity in the cluster halo, and a bridge of low surface brightness emission that is connecting the central halo with the relic. The bridge was studied in a paper that we published last year, and I won't talk about that here in this talk. I will focus my attention on the halo. So in order to understand what's going on in this cluster, we have to connect the non-thermal properties, so the radio emission that you observe, to the thermal and dynamical status of the cluster. And eROSITA data came out last year and helped us in this. The current dynamical picture that is proposed by this study is that there is a group, and you see 4839, that is crossing the Coma cluster. It should have injected a first shock during its first passage at the location where we observe now a radio relic, and now it would be bouncing back toward the cluster center after it's reaching the epicenter. While this group was moving throughout the cluster, the core has been perturbed, and the shock front is now detected at the edge of the radio halo. Okay, so to try to understand if we have enough energy in the thermal emission, how the thermal emission compares with the non-thermal one, so with the radio emission, we can use a comparison between X-ray and radio emissivity. So with the X-ray emissivity, we basically trace the thermal component of the cluster, because it is proportional to the square of the gas density and the square root of the temperature. here you see a mosaic of maximum Newton pointings. And instead, with the radioemissivity, we trace basically the non-thermal energy, so the square of the magnetic field and the particles, the relativistic particle energy. So one can divide the cluster into multiple sections and see how the radioemissivity goes with respect to the X-ray emissivity. And if we fit this slope, we derive an exponent of 0.8. So a slope of these two quantities equal to almost 0.8, which means that particles and magnetic fields decline lower than the thermal gas in the cluster. This can be also visualized if we divide the cluster into sectors. I have cut out the sectors where the bridge is because they would contaminate this analysis. And you can see that in all these sectors, there is something that is bringing the radio emission flatter with respect to the X-ray one. So we're trying to see if this trend can be understood with the help of cosmological simulations. We took MHD cosmological simulations that were published in 2019, where we found, partly by chance, a cluster that has similar properties to the Coma cluster. So it has a similar mass, and it is in emerging state similar to the one of the Coma cluster. And there are multiple levels of resolution that have been used in the simulation. And at the highest level, we have a magnetic field. Here you see for different simulations run with different resolutions, how the magnetic field increases. And we reach a saturation at the level where the magnetic field is a good approximation of what is derived in case of Coma. So just to say, this cluster, this simulated cluster, resembles the properties of the Coma cluster, not only dynamically, but also for what regards the magnetic field properties. So we took this cluster and computed the energy flux in the turbulent modes, in the compressive, and in the solenoidal components. And we projected this quantity. You see an example. You see these projected quantities in these two panels here, and you see that by eye they actually look different. And we have, of course, the compressive component that is dominating, that is stronger in the cluster outskirts, while the solenoidal one is stronger in the center of the cluster. So we were wondering, maybe if we look at how the X-ray emission of this simulated cluster what is the relationship between the simulated X-ray emission of this cluster and this energy flux that we take as a proxy of the radio emission. We can understand if we recover the observed scaling and if one of these two components presents a better fit with observations. So we did the same as in observations, and we found a slope that is comparable with the observed one in both cases. So this is a confirmation that turbulent can work to produce the radio halo in the Coma cluster, but unfortunately, being the slope very similar, this cannot be used to understand which of the two components is actually dominating the acceleration of the particles. We would need to do a more sophisticated modeling of the cosmic ray electron and see how, for different models, these two relationship would change. Another prediction of turbulent acceleration models is that the radio halo spectral index, so the spectral index of the radio emission, this should steepen if we go to larger and larger distances with respect to the cluster center. And this is because the magnetic field declines. So even if we have a constant acceleration efficiency, we should have that the spectral break frequency of the synchrotron particle should be lower and lower as we go toward the cluster central regions. And we took the Westerbork image published by Brown and Rodenk in 2011, sorry, and we took this LOFAR image, and we found that actually we detect steepening, although this is still a bit uncertain. There could be some instrumental effect that I'm still trying to figure out. Anyway, this could mean that actually we have another observational proxy that is in agreement with the prediction from turbulent models, and this could indicate higher efficiency in the cluster central regions. Finally, if we zoom out from the cluster center, since LOFAR has a very big field of view, we can see that there is a new emission found, an arc-like patch of emission that is farther out than the cluster barrier radius. It's almost 3.6 megaparsec from the cluster center, and it is in a direction where an optical filament of galaxies has been detected. So we tentatively associate it with the Coma cluster, although we have no actual probe that this is the case. But if it was, it would be very interesting because it could trace the reacceleration of particles due to shocks, similar to what we see in radio relics. But it will be a shock that happens, that takes place along the cosmic web. So here I'll finish with my summary. Low frequency observations now allow us to step into new territories to decipher the details of the particle acceleration mechanism in clusters, and we might actually hope to be able to discriminate which turbulent model better work, at least in the case of the Coma cluster. All the observations we have do agree with a run consistent with turbulent reacceleration, provided we have enough cosmic ray seed electrons on which turbulence could actually act. And this is one of the clusters that belongs to the LOFAR second data release that will be publicly available at the end of this month. So there are a lot of new discoveries that will be out soon. And so stay tuned for updates because there will be great news in the next months. And thank you for your attention.
Thank you so much, Annalisa. Thank you so much for the very interesting talk. Please raise your hand if you have any questions to Annalisa. So Federico, please unmute yourself.
Thanks, Annalisa. It was very interesting. Question about the one before last slide, the scenario where you observe in optical this shock on the upper left of the image. So doesn't this challenge in general the scenario of the reacceleration by turbulence second order Fermi with respect I mean, this shock doesn't challenge the turbulence reacceleration. It's not possible to have even fainter emission from shocks spread over even larger distances or different directions, so to explain and overcome the need of a reacceleration.
So you mean we should observe in the post-shock region some emission due to turbulence reacceleration?
Oh, no, of the emission at the shock, so a Fermi first order process.
The shock. Yeah. So in this case, it would be, I mean, if everything is confirmed, it would be Fermi 1 type acceleration. So it would be shock reacceleration of particles. Indeed, for relics, I haven't mentioned that very explicitly. For relics, what we think is that they are due to reacceleration by shocks instead of turbulence. And turbulence is now used mostly to explain the radio halo emission, because the spectrum is very steep. And in some cases, we observe a spectral index of 2, which can't be explained by shock acceleration.
So is it possible to have a larger number of shocks, not only this one here, but other shocks in different locations, which will provide the reacceleration you need?
Okay. Sorry. I understand the question. It would. I mean, it would, but it's not consistent with what we observe in both in polarization, because the radio halos are not polarized, and also in the spectral index, because the spectral index maps that we observe in halos are very patchy, while for shocks, we expect, as we see in relics, a trend of the spectral index being flatter when the acceleration happens, so where the particle is freshly accelerated, and then it will steepen in the post-shock region. This is observed in several relics where that actually seem to be produced by shocks. For halos, it would be actually more complicated because one should probably take into account all the projection effects. So I think really the point is that polarization is not detected in radio halos.
Yeah. Thank you.
So please raise your hand if you have further questions to both Annalisa and Stefano. So maybe Annalisa, could you introduce a little bit more about this LOFAR radio telescope to us?
Yeah, it's looking if I have a backup slide somewhere or not. Yeah, it's an interferometer. It's composed by several tens of stations. Most of them are in the Netherlands, so in the Central Europe, or north of Europe. And then there are other stations spread France, England, in Ireland. One will be built in Italy in the next year, and Sweden. So it's an interferometer with baseline that go from few tens of meters to 1,000 kilometers and allows us to have resolutions over several orders of magnitudes. The emission I was showing here is just done with the Dutch array. So with all the stations, it's 44 stations located in the Netherlands. Otherwise, if you include all the other stations, you would arrive to much higher resolution, so sub-arc second resolution. There was a paper out on yesterday, I think, on Nature Astronomy of data release where observations taken with the international telescopes were published. So with the international baseline with resolution down to a fraction of the arc second at 200 megahertz.
Very impressive, thank you. And I didn't see any hands here, so maybe we can stop here and I will stop recording. And